Hello, everyone. Thanks for coming. Let me start with apology. Sorry for the elevated number of Blade Runner references throughout this presentation. So today I'm going to talk about Blade, our Allen Telescope Array GPU accelerated beamformer that we are currently using in production at the Allen Telescope Array. So let's start by having a very quick recap from what is the Allen Telescope Array. So it was originally built from 2002 to 2007, and it was designed with astronomy purposes and also SETI, that is also astronomy, but more fine-tuned for finding search for extraterrestrial intelligence throughout the galaxy or galaxies. It's named after Microsoft co-founder Paul Allen that contributed in the beginning of the project. And recently it was refurbished for better system and reliabilities, thanks from the donations of lots of private donors, in special Frank Ling Antonio, that developed the new feeds that we are currently using. So here you can see the telescope in its whole extent. Here we have 42 antennas randomly distributed with a 350 diameter radius. Here, that house over there with the green roof is the signal processing center of the Allen Telescope Array. That's where all the signals goes with fiber, RF over fiber, and the signals are digitized and processed with our in-house data center that I will talk more about. Zooming in to the antenna level of the Allen Telescope Array, we have offset Gregorian dishes that are funny shaped dishes. Each one has 20 feet in diameter, or 6.2 if you're not freedom unit, and produce 1.5 gigahertz of bandwidth for each polarization. And we currently have true polarizations totaling 3 gigahertz, around 3 gigahertz per antenna. And that results, if you are sampling in 8 beats per sample, a data rate of close to 1 terabit per second for the whole 20 antennas that are currently operational. And one good thing about the Allen Telescope Array that we have a very large ultra-wideband reception area from 900 megahertz to 12 gigahertz. So that's a very wide band and very useful for multiple purposes. Now, where all this data is processed, so we have currently 8 dual-socket EPIC servers. Each one has 200 gigabits Mellanox fiber links, and also RTX 3090 or A6000 NVIDIA GPUs running CUDA. And also a relatively small NVMe cache, also working with PCIe X16, so we can buffer some data. So we are at a radio conference. I believe most of you know how beamformer works, but a quick introduction. If you have lots of elements distributed in an area, and you have a point source in the sky, the signal will arrive at each antenna at different pointing times. So you need to account for that if you are summing up all the signals for all the antennas. And that's what beamformer, our beamforming is doing. It's accounting for this difference and also trying to steer away from RFI and also other unwanted signals that can leak through our antenna. So that's where Blade runs. So let's talk about Blade. So Blade is a short for Breakthrough Listen Accelerated DSP Engine. Yeah, I tried there. And it's responsible for most of the digital signal processing of the ATA for the beamformer. And it's currently being used to process the data from the 20 antennas. And each antenna represents 3 gigahertz, as I said before, with 8-bit samples. And that equates to around 960 gigabits per second. Divided by 16 instances, we have 60 gigabits per second per instance to be processed. And that needs to be done in real time. So we don't store the data to be processed after the fact from raw data. We need to do this in real time, otherwise the data pool would be fairly large after some while. It's currently implemented 8 processing modules, ranging from beamformer channelization, that is basically a very large FFT, that I will talk more about later. And we followed some rules while designing Blade. That is, it needs to be performant while hackable, because you don't want a monolithic system that is very specialized on your target, but you also can't alter that without breaking everything, and no one knows other than the original person who wrote the thing how to modify that. So it needs to be modular and hackable at the same time. And also not to be afraid to use new technologies like C++20 and just-in-time compilation for GPU kernels. These are just examples, but if you are over traditional on the technologies you are choosing to build your application, you will find hardship where the new facilities can improve your quality of life. And also the low number of dependencies. You don't want your software to become unreliable in the future because some maintainer stopped maintaining your piece of software. Yeah. So this is a pipeline diagram, very simplified pipeline diagram. So the antennas communicate with the analog clusters that is composed of RF sock boards, that is Xilinx FPGA, with internal ADC that gets the signal from each antenna and digitizes that with the ADC and sends to all our clusters using 100 gig networking. Once it's in the cluster, we use HP Guppy. There's a legacy piece of software that will take the raw UDP buffers from the RF sock boards and upload them to the GPU. When the data is on the GPU, Blade will assume and do most of the DSP available for us there, and if necessary, return a pointer of the processed data to HP Guppy for later processing. The overall architecture of Blade is very simple. We have 3 main divisions. The first one is a module where all the GPU kernels are. That's where the DSP happens. And once you are trying to deploy this, you need a bunch of modules. For example, your data comes into a complex integer 8 from the antennas, and then you need to convert them to float 32 or float 16, so you can use ready-to-go FFT libraries like QFFT to do channelization and stuff. So you need a cast module, so you have a cast module. And then you need the beamformer module, so you can aggregate the antennas and reduce the data rate. You do this. We do this currently in float 32. The idea is to minimize that to float 16, so we get 2 times less memory and 2 times, ideally, less compute. So a factor of 4x improvement from float 32 to 16 that we are trying to implement in the future. And last, we have the Blade Runner that will take the pipeline and run it. So you need to have some assertions when you're working with a discrete graphics card, because 90% of our problems are data management and where the data is and where it needs to be. So you need to come up with clever ways to how to transfer data around, and Blade Runner was one of these ways that we developed. So once one pipeline is processing the data with the GPU hardware, the other pipeline is transferring the data to the GPU using the fairly slow speed PCIe 4 x16. That's our main bottleneck, and this segregated pipe runner with one processing, one transferring makes us around twice as more efficient, and our GPU utilization remains high throughout the execution of the program. Here is a blade module, so you can see it's a very simple module interface. You have the input struct and output struct. These input and output structs will define your pointers for your raw data. And also you have the generic config struct. So Blade was originally built to run on, built with running it on multiple telescopes. So you don't want to reconfigure your hardware, your software every time you need to change your telescope. So one of the design capabilities of Blade is to have a generic config struct for a channelization module, so it doesn't vary between telescopes. So you can use the same code on multiple telescopes. We're trying to use Blade on the VLA right now, other than the ATA for our SETI resources there. So this is an example of the config struct. It's just C++ with some flags there, and also numbers. We have the phaser. The phaser configuration module is very has like 20 parameters. It's very large because you need to specify where each antenna is and other configurations for the phaser. But this is one example of this. And then we have the input-output vectors. So we have a wrapper over a pointer, a GPU pointer, and a CPU pointer to facilitate our lives and make it less likely that we will crash the thing. So all the memory allocation and initialization is done when we start a program. After the Blade will process the first sample, no allocations, dynamic allocations are made. So we know that we won't have memory leaks or be inefficient by allocating memory that we already know that we need. So we just allocate it ahead of time and just run it, because remember, Blade can run with several days in each time, and it needs to be predictable on memory usage and also performance. So this is, for example, array tensor, and it's a templated, so you can send a device CUDA or device CPU and create, allocate CUDA or CPU memory using that. The newer version also has shapes, so you can modify the multi-dimensionality of the array using this API. Another good thing about Blade is that we do just-in-time compilation, because our kernels are very specialized, and we use templates and static parameters wherever we can to take the compute from runtime to compile time. So for example, if we are running with a sample of 10 antennas, we need to change the parameters, the number of antennas of the beamformer module. And since the number won't change during the execution of the program, we can do this in compile time and have a kernel compiled with just 10 antennas and optimize the register usage and other resources to run with the best performance possible. And we can't do this without just-in-time, because we would have to either compile all the possible combinations of parameters ahead of time. That would result in a very large binary, or we just need to recompile whole Blade again and again and again every time you change the parameters, which was not acceptable. So we use this just-in-time technology from NVIDIA, the NVIDIA runtime compiler. It's basically like NVCC, but it runs in runtime, gives you PTX. You can run that PTX whatever you want. Going in more details about beamformer, this is an example diagram of our current beamformer. So you have basically the dot product here that will do all the computations, and also the phaser module that will plug into the dot product module that will give all the spicy array to multiply with your data and give you the beamformed data that you are seeking. The phaser will take some time parameters like the Julian time and sidereal time, where the position of the object is, and we'll spit out the right phasers for the beamformer to be multiplied with. So here, another good one in Blade is the channelizer. So before Blade, we did this in a post-processing step. So we would do the beamformer and store all the data produced by beamformer, and then convert the data from time domain, pseudo time domain, to frequency domain in a post-process. And right now we implement that in Blade, so we can't do this in real time. What we do here is basically taking all the pre-channelized data from the telescope that is around, each block has 192 frequency channels and 8,000 time samples. So the end result needs to be all frequency domain, so 192 times 8,000. But then you need to do this over 300 seconds of data. You need to do this 64 times, so it's 64 times 192 times 8,000. So you are gonna every 96 megahertz. So expanding this with 3 gigahertz, 96, that calculations times 96 divided 3 gigahertz divided by 96. So you have a very large FFT. So 3 million beams FFT every second need to be calculated for this to be run in real time. So we just need to accumulate, or I mean, people need, accumulate. People sometimes think about integrations. Not integrations, concatenation. So we concatenate 64 blocks of 8,000 samples and do a very, very large FFT in the end. And we do this in every GPU, and every GPU has 96 megahertz. So in the end, we have a 3 million beam FFT. So that's a very large number, and we use lots of RAM, VRAM for this. And we also have other modules like Guppy file reader and the polarizer that will synthesize right-hand and left-hand circular polarizations from our horizontal and vertical polarizations, benzene calibration, and also correlator that we will hopefully have soon, and also a detector that will do the Stokes eye calculations from the data, and also a phaser that I just talked about. So this is an example of a pipeline. So you have a cast module, channelizer, beamformer, circular polarization, a detector, and a cast. This is one of the modes run by the Allen Telescope Array for generic science. And you can see that you can either take the input HP Guppy or another pipeline. So you can change pipelines together if you want. Next versions of the Blade will have a single pipeline. So modules that will change the ratio of input and output ratio can be stuck together. So this will be greatly simplified in the future. So you can have a concatenation module in line with another channelizer module, for example. It doesn't having to create a new pipeline. So that will be interesting, maybe next year here. And that's an example of a pipeline. Is just basically a connect, and you send a module, and it will connect. So here it's the main takeaways. It's fundamental to design the instrument to accommodate incremental changes without impacting the sky time. Otherwise, you're going to end up taking the equipment down just to change the software, and that's not something that you want. So something with modularity in mind, we recommend doing that way. And also, real-time processing will increase your efficiency, because if you think about this, if you are saving the data you are producing, you need to write that to your NVMe storage, and that write will pass through PCIe, and then you have the bottleneck of the NVMe itself. And then when you need to read that again, you need to do the opposite. So you're trying to read that PCIe again. So if you quantize that in energy used by just storing the data to process again, you're going to see that first you are murdering your NVMe. Second, you are spending more energy and time to process the same amount of energy. So a real-time process can give you more abilities. For example, if you need to observe something for a long amount of time, and you can't because you're limited by the storage size, you can use the beamformer with the integrator that will time integrate your observation and run that in real time for as long as you want. And your gains will be the factor of the integration. So you can run by several more time than if you're running just you're saving the data. So this is what I have for you, and if you have questions, you can contact me or ask right now. We have lots of time for questions. And also, Blade is an open source project, so you can go into this repository and look with all the code we have. If you want, you can do PRs. We like community helping you. You can also use Blade if you want. Just contact me or use by yourself. And thank you.
Thank you very much. That was a very interesting talk. Are there any questions for Luigi? There's a question over there. Do we have more microphones, or do you need to come your way? If you wait, then...
I don't know if this is out of your expertise, but the antennas looked like they were randomly placed. Are they?
Yeah, they are randomly distributed within like 300 meters of each other, and that's there's a good explanation why. If you have a very long baseline between antennas, you have very large precision, like the pixels of your phone. The pixels are smaller, you have more resolution, spatial resolution. But then you are very specific to one place, so you lose your focus. Your lens will have a more narrow field of view. So it's a balanced approach. So we do this because we are doing SETI and also others. If you like, I think Weil can answer your question offline better. But the gist of it is this.
Yeah, this is super cool. I had a quick question. How do you define the DAG of processing? Is that done in code, or do you have a configuration file that you then sort of jit out a graph? I'm just really curious how you organize these like components.
Yeah, so currently we do this in C++ files. Each module is instantiated in line, so The moment you connect the module into the pipeline, it will be instanced. And taking into account the inputs of the module, it will create the outputs with the same shape as in relation with the input. So currently it's C++, but I have another project called CyberEther that does that in a YAM file fashion, and they are very similar. Currently it's very static. We have bundles to bundle together multiple modules. So when we have modes, we call modes. It was a temporary name, but it stick around. It's called mode B. That is everything that you need to do beamformer, and we have a collection of modules pre-assembled for the user, so you don't need to wire together every time you do beamformer. That is a very common operation.
Are there any more questions? Oh, next please, yes.
I'm at your GitHub page, and I don't see the license that you're distributed under. It's screaming at me. Could you just touch on that?
Is TBD, but will be open source very, probably around some BSD MIT stuff. Thank you. Yeah. This was a trick question.
So next speaker already in the room, Bailey? Okay, that's good. Any more questions? I saw one over there. Probably last one.
Hi. You mentioned you use quite a bit of VRAM. I was curious if you had a minimum recommended amount for your GPU to use this.
Yeah. We have a very homogeneous system currently with RTX 3090s, and as you know, that comes with 24 gigabytes. And we are trying to make Blade reduce the number of gigabytes used by using in-place memory, so that will take like 2x less. But currently use 24. We are quite happy with 24 gigabytes. In the future, we will try to switch to a heterogeneous system where we have multiple generations of GPU in production at the same time. And for that, we will need to account for differences in VRAM sizes for 16 and to allow 48, or if NVIDIA releases something with good cost benefit, better, more graphics. In essence, with more VRAM, you can form more beams in the own sky. So it depends on your usage, but for us, 24 currently is enough.
Okay, thank you very much. Let's thank him again. Very good talk.